Okay, in this video I'm going to show how we get reduced coenzymes in ADH and FADH2 and ATP from a fatty acid through beta oxidation. We're not going to talk about the details of beta oxidation, but we will talk about it broadly and look at how many ATPs we can get based on the length of the fatty acid chain. So I have here a 6-carbon fatty acid chain, a carboxylic acid head, and a nonpolar tail. And so what happens first, before anything can happen with the beta oxidation, is the fatty acid must be activated. And the activation step basically means that a coenzyme A is attached to the carboxylate side of the fatty acid. And this actually requires 2 ATPs. It only says 1 ATP, but you can see down here that it is hydrolyzed twice, so we say that the cost is 2 ATPs. So the activation step, which only needs to happen at the very beginning, is minus 2 ATPs. And then what happens is the fatty acid is now activated and ready for beta oxidation. The first round of beta oxidation is four separate reactions, and we call this a beta oxidation spiral. And like I said, not going into detail on the reactions here, just going to look at it more broadly. And then what we end up with is the acetyl-CoA, which can then go into the citric acid cycle, and then the residual fatty acid that is still activated. Along with the acetyl-CoA, 1 NADH and 1 FADH2 is produced. In the next round of beta oxidation, for this one, is going to be the last round, because we essentially are going to end up with 2 acetyl-CoAs. Because this is now only 4 carbons in length, it gets split in half. And this is an acetyl-CoA, and this is an acetyl-CoA. So, and also, since there was one additional round or one additional spiral beta oxidation, there is 1 NADH and 1 FADH2, which are used in oxidative phosphorylation to generate ATP. So in summary, we had 6-carbon fatty acid, and we know that there's going to be 2 spirals. And I know this because 6 divided by 2 minus 1 equals 2 beta oxidation spirals. I know that I'm going to get 3 acetyl-CoAs out of this because this is 6 carbons, and we don't lose any carbon through this process. It's all retained. So an acetyl-CoA is 2 carbons long. So if I have 6 carbons to start off with, I know that I'm going to get 6 divided by 2, 3 acetyl-CoAs. So there are 2 beta oxidation spirals. Each one of these produces, so I'm going to do times 1 NADH and 1 FADH2. So that will get me 2 NADHs and 2 FADH2s. And remember though, the activation step costs me 2 ATPs. So I end up with 2 NADH, 2 FADH2s to go into the oxidative phosphorylation. These 3 acetyl-CoAs, these are going to go through the citric acid cycle. And if you watched my other video on glycolysis and the citric acid cycle, basically these acetyl-CoAs would come in right where the acetyl-CoAs come in from glucose. But of course this is not from glucose, it's from fatty acids, but they filter in the same pathway as they would if it was from glucose, because it's the same molecule, acetyl-CoA. So it's going to come in at the citric acid cycle, and then it will produce a certain number of NADHs and FADH2s. So from every acetyl-CoA, we're going to get 1 GTP. We're going to get 3 NADHs and 1 FADH2. per acetyl-CoA. So that means that we have 3 acetyl-CoAs. So we multiply all these by 3, and we end up with 3 GTP, which is really 3 ATP. We end up with 9 NADH and 3 FADH2. So let's put this all together. These are our totals from our acetyl-CoA that has gone into the citric acid cycle. These are the totals from the beta oxidation spirals. And then don't forget about the 2 ATPs from activation. So let's just write this out all together. 3 ATPs. We have 11 NADHs and 5 FADH2s. Of course, these, when we get to oxidative phosphorylation, ATPs is not involved, so these are still going to be 3 ATPs. NADHs, these are going to be multiplied by 2.5. So 11 times 2.5 is going to be 27.5 ATP. And then 5 FADH2s times 1.5 will give us 7.5 ATPs. We add all this together and we end up with 38 ATPs. So we get 38 ATPs for that 6 carbon fatty acid. Subtract 2 from activation. 36 ATP for 6 carbon fatty acid. Okie doke. So that is how you figure out how many ATPs are in or can be derived from the metabolism of a short fatty acid. Of course, it'd be much more if it was a larger fatty acid. Anyway, I hope that was helpful.